Hello everyone, this is Power System Class 3, Part 2. I would like to spend a few minutes over here to explain what's going on with the power factor correction. Before we understand power factor correction, we have to understand why inductive reactive power is positive and capacitive reactive power is negative. To do that, we have to go back to our equation of complex power, which is S is VI conjugate, right? So for inductive, let's talk about the inductive first. For inductive load, current is lagging, so your I would be is magnitude and a negative theta angle, right? So current is lagging. So now if I bring it back, let's say your voltage is with the zero angle, which is reference at zero angle. So now you come back over here to the equations. I'm gonna use this space over here. So it would be VI conjugate. That means your V is 0 degree angle over here, and I is conjugate, so it's gonna become positive over here, right? So then you have VI theta, right? So if I multiply them now, I get VI theta. So that VI theta is basically, if you express them in sine and cosine, it will be VI cosine theta plus J VI sine theta. So this is your positive reactive power. That is your inductive reactive power for the load. We're looking at the load, okay? So now, if I do the same thing for capacitive capacitive reactive power, so for capacitive reactive power, the current is leading, so current will be I leading positive angle, and I have same voltage there, so your complex power would be, again use conjugate, so that would be VI negative theta, because this would be conjugate, so it would be negative. That means I have VI cosine theta negative J VI sine theta. So this is negative, so that's why its capacitive reactive power is negative at the load end. What I'm talking about here, let me get a simple diagram here. I'm looking about a load here. So this is the V, this is the current going into the load. So I'm talking about the load and nothing else. So if it's a inductive load, your reactive power is positive. If it is a capacitive load, your reactive power is negative. That's what I'm talking about. All right. All right. So again, we're going to do this problem in the class. So let's talk about the complex power today. So I'm going to talk about the complex power today. What is complex power? So let's say that you have two interconnected voltage source over here, V1 and V2. V1 has its own magnitude plus its angle. V2 has own magnitude and his angle. And also we have a load over here, as you see, there's a load over here. So that load is Z, angle is gamma, all right? So the current going from source 1 to source 2 this way would be source 1 minus source 2 divided by the impedance. And in terms of a complex power, so if I take the I12 conjugate, I will get the conjugate complex power. So P12 and JQ12. So that's the power going from source 1 to source 2. And this is also power going from source 1 to source 2. So over here, if we simplify these two equation for P12 and Q12, this is for the real power going from source 1 to source 2. This is the reactive power going from source 1 to source 2. Let's talk about a line that is lossless. That means your Z over here is JX, right? If for lossless line, your R should be 0, right? R should be 0. Then Z becomes JX. So that means there is no real part. So angle is 90. It would be what? 90 degree. That means this angle over here, gamma we're talking about, becomes 90 degree now. So if that happens, it becomes gamma becomes 90 degree. This becomes 0, right? Cosine 90 to 0, right? And if this becomes 90 degree, this becomes sine. Okay, and over here this is becomes 1, right? And this becomes cosine. All right. So now with that, if we modify these two equations, then we'll get this for the real power, and this equation becomes for the reactive power. So if you look at here, your real power flow, this is magnitude, this is the magnitude, right? Your real power flow only depends on the angle difference between two sources, right? Source 1 and source 2, angle difference between them only govern the real power flow. And your reactive power flow, this over here, if these two angles are constant, then you have the voltage difference between two nodes will give you the reactive power flow. In reality, delta 1 is close to delta 2. It doesn't that not much difference there. So that this one becomes kind of 1. So this is become kind of 1 here. Then this your reactive power only depends on the voltage difference between two nodes. So here, so real power flow governed by the voltage angle. I think I have this in the next slide. So I'm going to talk about the next slide. So here, since R equal to 0, your R equal to 0, no transmission losses, real power received equal to real power sent. Real power flow mostly governed by the angle difference between voltage terminal, like delta 1 minus delta 2. And max would be when angle is difference is 90. There's a max power you can transmit, but you don't do that because you have to have some stability issue. So you don't go that far at the end. And so the delta needs to be around, the angle difference needs to be around 45 degree or less. And if that is constant, then your reactive power flow depends on your voltage difference between these two nodes. So here's the thing. Real power flow governed by the angle, and reactive power flow governed by the voltage magnitude between 2 points. So if you look at over here, so is power 1 and power 2, right? So for this graph here, you have to make sure that is voltage magnitude and the voltage phase for source 2 is constant. So we're not changing the source 2. So source 2 voltage is 100 and angle is 0. We're not changing the source 2. This is only source 1 is changing. So when angle is 0, look at the angle is 0 here. Angle is 0. So there is no power flow happening. There's no power flow happening between source 1 and source 2, all right? Because the angle difference is 0. Sine 0 is 0, right? So over here, on this side over here, source 1 angle is negative. So that means source 2 has the higher angle than source 1. So power coming from source 2 to source 1. The source 2 is supplying now. Up to this point here, source 2 is supplying. All right. So and when you go on this side over here, so your source 1 angle is giving positive, because source 2 is always 0. That means now your source 2 is supplying. So source 1 is supplying now. So source 1 supply, source 2 supply. So source 2 supplies when source 1 has a negative angle, because source 2 is always 0, so it's higher angle now, which is supplying. And source 1 has a positive angle, source 2 always 0, so source 1 supplying for this side. And this side here is source 1 is consuming. And this one is source 2. So this one is source 1 is consuming. And here source 2 is consuming. All right. So all depends on angle. Even the angle difference is delta 1 minus delta 2. Delta 2 is always 0, right? So for this side, when delta 1 is negative, delta 2 is 0 is higher, so source 2 is supplying. On this side over here, when source 1 angles become positive, then source 1 is supplying now and source 2 is consuming. All right. So we're going to do this problem in the class. And that's all for this lecture. We're going to talk about Powerwall in the class a little bit. So here's the take away from this whole class is that your power factor correction, basically your loads are inductive. So you need some kind of capacitor coming in parallel with the load to minimize the angle between current and voltage. That's the power factor correction. How much you need to, how much capacitor you need, that means that needs what is the inductive power out there, and how much inductive power you need to compensate with the capacitive power. That will define the capacitor as well as the line voltage will define the value for capacitance. We're going to do the problem in the class. And for the complex power flow, real power flow only depends on the angle difference between two sources. So if angle difference is, the source 1 has higher angle than source 2, then power will go from source 1 to source 2. If source 2 has the higher angle, then I'm talking the voltage angle here, then source 1, then power will go from source 2 to source 1. Reactive power flow depends on the voltage magnitude. So if the source 1 has a higher voltage than source 2, reactive power will go from source 1 to source 2. If source 2 has the higher voltage than source 1, then reactive power will go from source 2 to source 1. There's the summary for lecture class 3.